Greetings and welcome, friends. Taking a look at last night's homework, page 915, for the second time. But yesterday we were specifically talking about standard deviation, both for a given list or set of data, as well as in a frequency distribution. Here's problem 17. We're starting this a little bit backwards, I guess. But standard deviation for a frequency distribution. Let's see if I can even write this whole thing down. Here's what the formula is. It's the sum of I equals 1 to k of the square of this difference, xi minus x bar of course being the approximated mean within that frequency distribution, and you multiply that by the frequency, and then let's see, then we divide by the sum of I equals 1 to k of fi. And this is the formula that we have for this. So in order to get this calculated, I could do this all by hand in a table, but fortunately I equipped you guys with an Excel spreadsheet last night as well. So here's my Excel spreadsheet. The thing that I had to change was the class started at 1, because you can see that it starts at 1, and the class interval was 4, so I changed that value. And then I plugged in all of the frequencies for their corresponding classes. And let's see, according to this formula, I'm going to want to take xi, which in this case is not representative of an individual data point, but it's representative of the class mark, right? So the class mark from 1 to 5 is 3, all right? And what I'm going to do is take the class mark 3 and subtract the mean, and x bar, the mean, also an approximation, like I said, is 19.33. So I'm going to take 3 and subtract that mean, and I get all of these different values, right, for all of the separate values of xi. The mean was the same for all of those. And then I square that difference, and that's what I have here. And then I multiply that by the frequency. So multiply this by my cell E4 here, and that's what we've got going. So you can see theoretically, yep, you can see that that formula is calculating correctly. And now that I've multiplied and differenced and squared all this stuff out, the sigma tells me I want to take the sum of all of those. So all that means is add up that whole list. And you can see that I have in fact sigma'd that, right? I've added it all up. I've summed it. So I've added this list. And now what I'm going to do is divide by the sum of the frequencies. And what's nice about this portion of the formula is I just want to point out that this is the part where in mean deviation or standard deviation we divide by n, right, or multiply by 1 over n. This actually is 100% guaranteed to equal n if you wanted to know the number of terms. Because if I add up all of these frequencies, that is going to equal the number of terms in the entire set of data. It's not an approximation, is my point. So the sum of the frequencies, well, I believe happens to be this 120 here, right? I've added up this list over there. So I'm going to divide those two and square root it, as any good standard deviation formula would do. So I've done that, and here is my estimated standard deviation. 6.4825 is my approximated standard deviation right there, and it's an approximation for a frequency distribution primarily because for these 8 values in this class, let's say, I didn't know whether some of those were 5, some of those were 8, you know, some of them could have been 7. So we've gone off of the assumption that all of those average out to be the class mark, the middle value there. And then also you can see that they did ask what the mean deviation was, 19.33, the x bar, and we did have that as well right there. So we could also write that 19.33 as well. So there's problem 17. That's calculating standard deviation. It's a measure of variability. In a sense, it's kind of measuring the same thing as mean deviation. It's the average distance that any of our data points are from the middle. Okay, so since my mean is 19.33, my standard deviation 6.4, that's not varying too significantly because, you know, 6.4 is you know, not even half of 19.33. So it's, you know, some points are above, some points are below, but they're all roughly around that, and this number gives me an idea for maybe the density of my data, I guess is how I'd say it, how closely the data is to the mean. So here's another problem, a lot more for us to look at on this one. It says, during a recent season, 7,684 teams played 19 NCAA women's sports. The breakdown of these teams is given below. So this isn't scores or anything. These are actually 966 basketball teams. That's a lot of teams. Wow, 42. Wow, I didn't know you could have a fencing team. I don't know enough about that sport, I guess. Huh. I imagine that it's still probably some sort of one-on-one brackets, but you just have a team of fencers, I'd imagine. But anyways, it says, what is the median number of women's teams playing the sport? So I'm going to flip on over to the Excel spreadsheet once again. And I've actually got this little box and whisker graph. I ended up programming this yesterday. And it's going to auto-calculate most of these things for us, and I'll explain how it does it. You can see I actually have some hidden formulas right there. I can kind of shrink these down a little bit. Whoa, not too much apparently. I just want to kind of have it, let's see, and I think I can stretch this out here. There, that's fine. So let's populate this list with the actual number of teams from that woman's list. So here we go. So here's that data, and if you notice, it's not in order, but we could sort it A to Z if we wanted. So there we go. So if I want to find, if I want to find the median, what's another name for the median, by the way? The middle number, that's the definition of it. In terms of box and whisker plots, what's another name for the median? Yeah, quartile 2. So I could call this quartile 2 or the median. And you can see that I've found the median. It's 282. And it's just the formula in Excel is median of that list. So if I look at this list, the median number is 282. That means that it must have had an odd number of data points, right? If there's an even number in the list, actually I can hit equals count A3 to A103. So yeah, there's 19 data points, so the middle number can have an even number on both sides. If there's two numbers in your middle, so to speak, if you had an even numbered list, then you would just find the midpoint between those two. But this one didn't have that problem. So that's the median is the 282, and we agree with that. Yep. Then it says find the first quartile point and the third quartile point. Now I've programmed this as well, where it did correctly find that, and you might say, well, where's it getting that information from? I actually ended up programming it so maybe I will show you the behind-the-scenes stuff here real quick. Why not? Why not? Let's see. Where's my toolbox? Change some font color here. And there we are. So what I ended up doing was I made a list of the first half, so to speak, where I just basically said, is this less than my quartile 2? All right, that's all the logic you have to understand from that. And then for the second half, I said, is this greater than my quartile 2 point? And notice quartile 2 point lands in neither half. Okay. However, what's cool is if I added, say, we had one more sport that had 1,000 teams, then the median, so to speak, quartile 2, would have been between those two values, and each of those values individually would have counted on their own half. So I just want to point that out. So quartile 1 is just finding the median of this list. Quartile 3 is finding the median of the second half of the list, and that's where I'm getting 770 and 42, which is correct. Then it says, what is the interquartile range and the semi-interquartile range? What's the formula for interquartile range? You guys remember? Q3 minus Q1. So I call that interquartile range right there. There's 728. So you can see that. Semi-interquartile range. You remember what that one is? Yeah, it's just that divided by 2. So there's the semi-interquartile range. Normally we don't actually need the semi-interquartile range that much. But there we go. And then related to the interquartile range is outliers. Now outliers were any data points below quartile 1 or above quartile 3 by a magnitude of 1.5 times the interquartile range. Crazy definition. Let's explain it out. So I ended up taking my interquartile range and multiplying by 1.5. All right, 1092. And then I said, well, my lower bound would be quartile 1 minus that 1092. That's where I got here. My upper bound would be quartile 3 plus that 1.5 times the interquartile range, 1862. So any outliers would have had to be less than this number or more than that number. And you can see in my list of outliers, I actually have that all programmed in as well. It's just saying, is it less than this number or greater than that number, and then giving me the number. And there are no outliers for this list because they'd have to be beyond those boundaries. So that's not an issue for us. Part E says make a box and whisker plot. Now I did end up coding this. Unfortunately, this won't code in what's it? It won't program for the current form of Google Docs, sadly. Let's see, I think I can change the scale to, oh, did I just mess that up? I thought I entered 1,000, but apparently I entered 100. There we are. So I've kind of zoomed this in. So here's my box and whisker plot. Let's actually grab a snapshot of that and we'll draw over it if we want to. So here's my box and whisker plot. Your guys would look something like this as well. And just to verify that we all know what goes on with a box and whisker plot, this is your lowest point. This is quartile 1. This is quartile 2 slash the median, right? Same value. And this is quartile 3, and this is our highest point, right? So this is my box and whisker. You do have to have some sort of a number line there. So if I wanted to actually find that value, I would just go down. Let's see, what did I say quartile 1 was? I think it was 42. So that should land somewhere around 42. Quartile 2, we said earlier, was 282. Seems to be in the right spot, right? So it's got this all mapped out. And the value of a box and whisker plot in terms of measuring variability is that each of these locations represent 25% of your data. All right? So you can see that this region right here, the smallest little region right there, represents 25% of the data. So I would say that the points between quartile 1 and my lowest point are very densely populated, right? 25% of the teams are between those two values, right? Or I could say 25% of the teams are less than 42 in the number, right? Or sports have less than 42 teams in them, is what I'm saying there. So it's really densely populated there. The least populated region is between quartile 2 and quartile 3, right? Because that's the broadest set. And if that's got the same amount of data as that, then this data must just be really sparse and spread out, where this data is just really, really clustered together here. And if we look at our original list, you can see that we do actually have a majority of our teams are all kind of tightly knit there. And then for the next set, these ones start spreading out more. These ones spread out even more, right? That covers a much larger range. And then this range is not quite as much. So that is some sort of data that we can analyze as a result. So there's our box and whisker plot. Let's see, then it says, what is the mean of the number of women's teams playing the sport? Let's see, what did we just lose? Whoa, we just lost power there for a second, but it's working.
Still can't find out which one it was that you used.
Let me see.
I tried playing around with it, but it's not the same.
I wonder if I could search for both.
I found one, but it wasn't the right one. I got about 1,000 emails from you.
Yeah, that's true.
So I need to keep all those and get rid of some.
Wait, didn't we add didn't you have
my drive right here, but I couldn't.
I thought we added it
I
somewhere.
did, but I
in
don't think we did the
bookmarks.
final version. We got rid of it. Henry,
Let me send you an email real
Okay,
quick
so-
right now.
December 4th. Can you do it on December 4th?
I think so.
And I invited Tristan too, so he come along and support you a little bit. We'll blame it on him if it doesn't go well. No,
Let's
it
see.
won't.
Evaluation
So
system.
we'll get, you do a little PowerPoint presentation?
Mm-hmm.
You got a laptop and everything?
Yeah, I have one.
Okay, and you need, they have a projector, is it IBM or a PC or is it a Macintosh? PC? I'll bring mine too, just in case, okay? It only has to be like 15 minutes.
All right, let's see. And hyperlink this in there.
That's what we should do, Colin, you know, I was just thinking, we should have all the, I should tell them that I want to invite all the whole soccer team up to the Rotary Club meeting in the morning for a breakfast meeting. You know, what, would you guys do breakfast, eat in the house, okay?
All right, I think I just sent you an email with the link. It should work out. So let's see, where are we? It says, what is the mean of the number of women's teams playing a sport? So this isn't a frequency distribution, so this is going to be an exact calculation, which is nice. I'll be able to just take my list, right, and I'm going to put this into my list version for calculating deviations, variability, and I enter this in, and it calculates the mean just using the straight up average formula from that list. So 404.42 is the average. The way we calculate the mean is we add them all up and divide by how many there are, right, is literally how we do it. Then it asks, what is the mean deviation? So remember, mean deviation is a measure of variability. Mean is technically a measure of central tendency. This is measuring where the middle of the list is. This is measuring how varied the list is about that middle, right? So that's what that's trying to describe. So mean deviation is talking, let's see, here's my mean deviation, and it's calculating the average distance each data point was from the mean. All right, so I found, I've got that formula. It takes the sum of those distances, divides by the sum, or the total number of values in the list, and calculates it out, and 316.969, I guess I should round that up to, yeah, that's just going to be 317.00, right? All right, they must have just, or okay, they rounded up to 2. Yeah, that works as well, definitely. So 316.97, and that's not an approximation. That is, well, it's an approximation because they truncated the decimal there, or rounded the decimal, but that is an accurate measurement of mean deviation. There was no assumptions about those data values. We knew the exact data and were able to calculate that. Now, actually this word variance is related to standard deviation. We didn't mention that yesterday. We'll come back to H in a second, but I says what is the standard deviation of the data? Standard deviation is similar. Instead of taking the absolute value, we square those differences, and then we square root after we divide by n. Standard deviation, like I said yesterday, is going to be a little bit bigger than mean deviation typically. But yeah, so it's you square root and then divide those two things. So the real only difference between them is I'm dividing by the square root of n. Actually, let's test this theory. Let me do this right here. Equals, let's do this number divided by the square root of n. And in theory, I believe, no? Okay, apparently not. I'll have to reconsider my theory. I didn't do that. Did I plug it in right? D1, the sum? Huh, I don't know. I'll have to go back and consider the mathematics of that apparently. But anyways, if we follow the formula right, and not my crazy shortcut that didn't work, this is what we get, 344.55 when you round up, and that is what they get. Now variance is actually denoted by sigma squared, little sigma squared. So if we just take this and square it, that's how you get variance, okay? So that's worth pointing out. Variance is just another statistic. It's just equal to sigma squared, standard deviation squared. It's just another value to try to have an idea about the variability of the data. So there's a lot of individual little measurements that they have to try to quantify How spread out is this data? That's all that it's doing. So after looking at all of those values, J says discuss the variability of the data. So to analyze the variability, the box and whisker plot's a good point. Mean deviation's a good point to look at, and standard deviation's a good thing to look at, right? And variance, in effect, also discusses the variability of the data. So what I would say, let's see, I would say that the value is less than quartile 1. And Q1 are densely populated. Let's see. I'm not sure if I need another E on that. There we go. What else do we have? Let's see, the mean value, what was Q2? That was the 282. And
I'll stop now, see you later.
the variability is 344. So the standard deviation is actually greater than the mean. So that means it's actually jumping far away from this rather quickly. So the mean deviation and standard deviation sigma are greater than the mean. Then the mean, I guess I'll write mean rather than x bar, suggesting the data is very spread out. Suggesting, I guess, on average, the data is spread out. Okay, let's see what the book actually said about this on 22. They usually have some sort of explanation. They said there is great variability among the number of teams in women's sports. Come on, guys. Give me some details. Well, that's good enough, but I do find it actually really interesting, this little region right here, densely populated. We didn't have a lot of data points, only 19 to go off of. So yeah, if there was more sports teams and stuff, or sports to have considered, you'd have more data values and you could go from there. But that's the idea. Talking about measures of central tendency, the only one that we actually had in this case was the mean. The rest of this is all describing, well, actually, I guess quartile too. Yeah, median is another measure of central tendency. The rest of the data here is all talking about the variability, how spread out it is, right? Outliers, you could even think about, are a type of it's describing the variability of a single point. Like this point is so far away from the rest of them, right? That would be a case of extreme variability, at least for that one data point, where there was no others necessarily that were clustered with it. Or comparative to the most of the data, right? Most of the data would be elsewhere. So thanks for watching, Internet friends. Have a great day. Bye-bye.